Okay, welcome back. We discussed PSRR in quite some detail for an LDO. It is good to see some small pictures, an expression that will sort of connect and give you some idea of how this PSRR is an important thing. I will not go into great detail, but you must know where to find material so that you can sort of locate it yourself and read, do some self study by yourself. Let me point you, this is about a document which I got from Tech Days. Okay, this is from Texas Instruments. I can share this document, you can actually download this document. This picture is nice because it is telling you the expression for PSRR. This is 20 log of V in AC divided by V out AC. It says V in AC. Okay, this is not DC input, this is more the fluctuations in the input that appear at the output of the regulator. So please note, this is not the DC component. We know that it has to be superly DC output, low noise, right, but the noise is because of the AC component in the input signal, and that is what he is giving you, 20 log of V in AC by V out AC. Okay. If it was indeed a straight line at this point, you would get a straight line here, which is basically the V out will be less than the V in and everything will be hunky dory, right, but that is not the case. Unfortunately, there is always some ripple at the input, and that is the ripple that he is showing here. It is talking about how much you are able to eliminate this ripple at the output. This looks a good picture, right. You have huge variations in amplitude here at the input, you have a smaller variation at the output. So what is the definition? Ability represents the ability of the LDO to filter out input voltage changes. This is critical for low noise applications, very critical, because this can affect, if you give this output to a VREF of an ADC which is doing some sensing application, then this will appear as a change in the reference voltage. Remember, we discussed that. So be careful about the output of the LDO to what you are feeding the output of the LDO. You do not want to mess up with that, because it can create a noise pulse, noise at the reference of even an ADC here. Okay. So this is one thing. Then this picture is telling you something little more important than the LDO. We will come to that though, but it is good to tell you this straight away. And this picture is telling you DC-DC converter noise is way beyond that of a LDO noise. Okay. So and you can see that DC-DC behaves even more peculiar at a slightly higher frequencies. So first of all, remember, this is a log plot. The best way would be to do all your buck conversion from higher voltages to almost what is required using DC-DC, and feed the output of the DC-DC to an LDO and get back this configuration, essentially this configuration, right. So you can say that this is coming from DC-DC converter, and what you get output will be pretty smooth, provided you pass it through the LDO which has a high PSRR. Okay. So essentially that is what this is actually telling you. You can see that switching regulator is the input, and it connects to LDO which has quite a high PSRR, and then you get the output out there. So anytime you want to do some noise filtering, it may be good to pass it through an LDO. Okay, it is like a noise removal. Then these are the regions of the PSRR which he talks about, region 1, region 2 and region 3. How the region 2, the effectiveness of the open loop gain of this error amplifier, which is so important in its ability to keep the output voltage at the right point, is also mentioned. Then this picture goes on to talk about what are the conditions that affect PSRR. He talks about one, then the next, and the final thing. Then what are the conditions that do not affect PSRR? Number 1, what is it? Number 2, what is it? And number 3, what is it? I encourage you to strongly read up on this document, and which will tell you a lot more about selecting your LDO of your choice for certain applications. And well, This picture is also well known to you now, that this is the series pass of an LDO and this is the error amplifier, these are the sensing resistors and so on and so forth, and you can see that the V out is nothing but Vref multiplied by this term here, which are the 2 sensing resistors, and that is what your V out is usually held at. Okay. Any noise on Vref is gained up. So, if you mess up the Vref of an LDO, again you are going to have a trouble. So, your own Vref should be extremely stable, and the output, if it is connected to a Vref of an ADC, even that is going to be troublesome. So, careful with output voltages, extremely important to keep them under low noise condition. Alright, so we will close the discussion there, but we will move on to other important aspects of an LDO, and we will look at what is known as this transient responses. Okay. I want to point you to the understanding of this transient response. See, transient response is what is the effect of the LDO's output. This is your C in, this is going to the LDO, this is your C out, this is V in, and this is the load resistor, right. This is V out, this is your V out, like a block diagram. Okay. The trouble is you always want the V out to be held at a fixed point, but what actually happens is the load currents, the load current keeps fluctuating depending on the state of the IoT node, right. Sometimes it may draw 50 milliamperes spike in 1 microsecond, sometimes it may draw only 20 milliamps in 1 microsecond, sometimes it may draw 150 milliamperes in 1 microsecond. You can see this di by dt is the trouble creator for you. Okay. The di by dt, of course di by dt is highest in this third case. So, in spite of a higher di by dt, you do not want the V out to move up and down at all. That is what you mean by transient response, right. And you may want to say that transient response of 150 milliamperes per microsecond keeps the V out is within 50 microvolts. It is a good thing, right. So, you will have a spec like that, and this is what you should look out for in the data sheet. You do not want it to go more than that. That means even under huge transient. Why is it transient? Because the time it takes to consume this to draw this 150 milliampere is quite short. In 1 microsecond you are drawing 150 milliamperes. After that it may settle down, that is another story, but that should not pull the LDO out of regulation, and that is essentially what you should look out for. Alright, so now we have to see how these things are defined, and this data sheet, this little discussion I was trying to do is essentially talking to you about this particular transient thing. Transients can be improved by putting a suitable output capacitor. Okay. Many LDOs require a large external capacitor to be placed, so that loop stability, transient response improvement and lowering the noise bandwidth, all these are possible, but then this becomes an additional component. Your IoT node size may increase. So, that is one part. Then of course packaging, then there is ESD related issues which you must read carefully, and selecting the right LDO means you must look at mainly the datasheet parameters that we described, because essentially you are powering RF circuitry like as VCOs, mixers, PLLs, of course ADCs, okay, they all need very low noise in the frequency bands of interest, and so you may need very good noise rejection. And also you must ensure that the low PSRR in higher frequency ranges can become an issue because they directly translate to channel jitter and intermodulation distortion. So power supply is indeed a troublesome block even in an IoT node. I just want to point you to this point of jitter. You can see that low transients up to 150 milliamps per microseconds, right, with less than 45 millivolt. Yes, just put a number, I put some other number. In fact I put microvolt. He says I do not think you will get even 50 microvolt, you will not get this, you will get 50 millivolt. So that can be, I mean the lower the better, right. If you get 50 microvolt, maybe it is magic, you may not get that. More practically it will be about 50 millivolts. So do look out for 10 millivolt, 20 millivolt, 30 millivolt and so on for this load currents, transient currents, that is important. So typically 150 milliampere per microsecond is giving a number like 50 millivolts at the output. A change can relate to 50 millivolt, which will be quickly offset, but that may not, again it depends on your application. So what is very important is it may not impact so much, but it may also depend on your application. Now to ensure that the current transient will not matter too much for your output voltage, you have to choose the C out capacitor accordingly, so that it is able to give you that, deliver that power instantaneously. All of this has to be borne in mind. In summary, these are the parameters of great interest to you. So let us run through them, and this is the same that you saw in the other data sheet as well. Input minimum, typical, maximum. Output voltage programmable from 0.8 to 3.3 volts. Output voltage accuracy plus minus 1%. Dropout voltage 40 millivolt at 100 milliamperes. If you are drawing a load current of 100 milliamperes, you will have a minimum drop of 40 millivolts. All you need is 40 millivolts drop. But if you draw 300 milliamperes, the dropout voltage you have to maintain is 90 millivolts between the input and the output. Okay. This particular LDO which has been shown has an output load current of about 300 milliamps. Output load capacitance 4.7 microfarads. Load regulation units, see carefully, it is millivolts per amp. Unit is millivolts per amp, 2 millivolts per amp, just changes by 2 millivolts per amp. Remember, load regulation is different from the transient response. There it was so much of current in a given microsecond, huge spike in current drawn. Here it is for every 1 amp change in current, the load regulation is about 2 millivolt per amp, provided you are talking about 1 milliampere to 300 milliampere and a C out value which is about some capacitance value. Okay. Now look at line regulation. Line regulation is mentioned in 5 millivolt per volt, it is not amps, it is millivolt per volt, and this is about 5 millivolt. And the conditions under which line regulation is offered at 5 millivolt is V in should be whatever you draw at the output plus 0.5 volts, that is 500 millivolts. You must maintain that. If you do that, you will get 5 millivolt per volt in line regulation. Then shutdown current is mentioned, then power supply rejection is mentioned. Okay. These numbers are just about okay, 40 at 10 megahertz 40 dB is okay. Remember 10 megahertz and current drawn is only 100 milliamperes. For 10 megahertz, but if the current changes to 100 milliamperes, but the output capacitance that you have some other value, then you will get up to 55 dB. So these values that you choose have a huge impact on the power supply rejection, and this is very important to be borne in mind. Okay folks, so then you have other parameters which you may want to effectively use for your design parts. Let me now point you to this data sheet, load regulation under light loads. When you say light loads, you are talking of 0 to 5 milliamperes. Here you can see this is 0 to 150 milliampere. Then you have line regulation which is shown here. This is delta V out which is shown on the y axis, and you have V in which is shown in the on the x axis. So we can look at line regulation when the current drawn is 5 milliampere in this case, and when the current drawn in this case is 150 milliamperes, that is what is mentioned here. Let us look at this load regulation under full load condition. You see now the load variation, okay, if you draw 150 milliamperes and you are at sufficiently high temperatures, let us say you have kept the LDO in as part of a circuitry placed outdoor, and under that outdoor condition the temperature has gone up, surrounding temperature is at 125 degrees, the output voltage will drop by minus, that means it is dropping down, isn't it, is dropping down to anywhere between 35 millivolts to 40 millivolts, that is what it says here. Whereas if your temperature is at 85, it is not dropping so much, it is dropping to minus 20 millivolts. Supposing you have 5 volts at the output, you will be 5 volts minus 20 millivolts, okay, that is what it means, will be your output. Similarly this picture, so you always can substitute these numbers with whatever is your output voltage, that is why it gives you the delta V out, that means you have some fixed output voltage. Now what has happened is it has come down, the difference he is plotting here, okay, that is what he is plotting here. This is the important thing, so difference will be so much. Same way if you go and understand this picture, you will see that at room temperatures 25 degrees and so on, drop is only about around the minus 10, even less than minus 10, right, and it is little bit negligible if the temperature is at minus 40. Supposing you place the LDO part of an airplane, okay, and it is exposed to outside ambient, your embedded node is collecting data from an airplane at minus 40 cruising altitude so you get minus 50 minus in that range, then there is hardly any drop in the output voltage even under high excursion of current being drawn in some sort of very short duration. So it will be telling you that under full load as well, negligible change at minus 40, which is extremely good as a load regulation system. You can interpret similarly for light loads, and you can interpret similarly for the line regulation as well, okay. You can see these pictures. There is a significant problem with the line regulation at high currents. You see 150 milliampere, there is a drop, whereas under light load conditions you do not see any problem, line regulation is very good, in the order of minus 0.2 and so on. That means it is down, not up. Minus is simply indicative that the output voltage is going down, and that is very small, insignificant at very high temperatures. Whereas if the current output current drawn is in the range of 150, you will see some real drop up to about minus 2. Here it was 0.2, here this range is from minus, it was in the 0.2 range, and here it is in the minus 2 range. So please note the y axis here and the y axis here, they are different in terms of the markings. You can go on like this, read about this data sheet, interpret several interesting things. Now you can also look at the dropout voltage versus output current. Okay. You can see that it can be as high as 220 millivolts, okay, the dropout voltage, if you are operating the LDO at 125 degrees at full load current. That is important. Okay, so that this picture is saying that. So you could go on interpreting these view graphs and use them in your applications. If you have to design something, you have to use them. So please, I encourage you to read these view graphs and understand them better. Similarly, PSRR versus frequency are interesting plots. You can see that higher frequencies the PSRR drops, and you have to somehow find a solution if your input indeed has input high frequency inputs and you want to circumvent this problem. Okay. There is also pictures related to junction temperature. These are very important. The junction temperature comes directly from the fact that the current consumed, if it increases, the heating of the IC also increases, and it adds to the ambient temperature, rise in the ambient temperature and also rise in the junction temperature. That in turn has an impact on the stability of the LDO itself, right. This voltage, the LDO can start having issues with respect to the temperature if you do not choose the right kind of package for your application, right. So this is one part of the story. I will also take you to another part, which is perhaps the last item under the LDO. Let us just do one small bit and concentrate on this picture, which is so important folks, so important, and this is how you must design your IoT node. Okay. This is a must kind of thing. Okay. This picture is powerful for a different reason. Forget about the company, the ICs that are shown here. The layout is really good. Look what is expected. You are interested in, you have a high voltage, in our case we are talking in IoT parlance, high is already 5 volts. You are interested in stable 3 volt output, okay, and the current drawn is going to be about 200 milliampere. This is your input, this is what you want to step it down to. Okay. Now if you want to get 3 volt at 200 milliampere, you do not want to go very high, right, you want very close to 3 volt to be as here, so the dissipation across this can be reduced. So what does he do? He brings 5 volts down to 3.3, and that is what he takes as a tap out. This tap out 3.3 volt system is to some extent does have a ripple, there is no doubt about it, it has a ripple, but then by magic he feeds this ripple input to this LDO, but before he does that he passes it through this block. This block does all the magic, and what does it have? It has an inductor which you can buy in the market as high frequency beads. They are available. Look up data sheets on high frequency beads. In essence, it is an inductor and a capacitor, essentially like a filter. You filter out the high frequency components and then feed it to this LDO. Now you get 3.3 noise free, ripple free as an input, and then you will get 3 volt 20 milliampere maximum load current, which can be directly connected to highly noise sensitive systems like tuners and so on. Okay. This paradigm you should never ever forget, folks, never ever forget. I must tell you that you must sleep with this picture in your mind, that LDOs typically you must have a difference in input to output which is not more than 0.3 or 0.2 volts. Of course, that will depend on your load current on the right side, but typically the difference is very low. So that power dissipation of the LDO itself is low, and if you have a higher voltage source, the best is to come down to as close to the output of the LDO with a difference of whatever that the data sheet tells you. Come down with a buck converter. This is a buck converter, folks. You see this left side picture, this left side is a buck converter. It has brought it down from 5 to 3.3, and from 3.3 after this filter action you are getting 3 volts. So this is very important. This picture is actually capturing everything and it is self explanatory. You get 3.3 volt with a lot of ripple, okay, 11 millivolt peak to peak in light load, 30 millivolt peak to peak with the transients. It is really bad. Look at what happens at the output, 1 millivolt peak to peak. How did you do this? Exactly by this trick, by removing it with a high frequency bead. So this is a very important design requirement in this course. Please remember this picture, read this as much as you can and understand the LDOs to the best possible extent. Thank you very much.